much. Thanks for coming. Good afternoon. So today I'm going to talk about interpretations, as many of the other papers will, I guess. In particular, we'll look at how we can evaluate these interpretations in the context of human-computer cooperation. I'll explain what cooperative play means in a bit. So I'll start with this obligatory slide about the success story of machine learning. We know that with a large amount of data and a lot of compute, we can train this system to do amazing things, like playing Go, playing StarCraft, doing image classification, speech recognition, machine translation, and so on. So that's very nice, but it's also well known that in its current state, the drawbacks and limitations of machine learning are still very significant. For example, if we use it for recidivism prediction, the system called Compass will famously make this mistake by classifying the person on the right as having a higher risk, despite all the evidence that says otherwise. Right, so fundamentally we humans care about things that cannot be easily captured by the computational objective of machine learning. For example, we care about things like accountability, transparency, fairness, but essentially these like supervised systems only care about minimizing several loss terms, right? So we may not want to replace humans with machines. Instead, we want them to work in cooperation. Especially, we care about this human-centered setting, where each input is shown simultaneously to a model and a human, and the model will make a prediction, show this prediction to the human, and it's called human-centered because we have the human make the final decision. So this is kind of a way to circumvent the issues of like fairness, accountabilities, and stuff like that. So one thing to note here is that in like the traditional approach of evaluating machine learning systems, we only care about the system output. And the model performance is basically evaluated based on comparing your system output and the label. But however, model is only part of the system here. And the thing we actually care about is the decisions that human make. And we care about the human performance, right? So the goal of including a model in this setting is to augment the human decision-making process and eventually improve human performance. The second thing to note here is that it's not immediately clear what we mean by this arrow. So how exactly can we communicate the predictions from a model to the humans? This is not trivial, right? Because, for example, given a question, who invented the mouse? A question answering system typically outputs something like, I am 70% confident that this is dog Engelbart. So this might be useful enough for the crowd, but it might not be so useful for someone without domain knowledge, right? Based on this number, it's very difficult to decide whether or not I can trust the model prediction. So what we do instead, and which is quite popular in the community recently, is using these interpretations. And what they do is essentially explain the model prediction in other aspects beyond this just the label and the confidence number. For example, it takes many forms. The first form we consider is showing alternative answers. For example, the system can say, okay, other than this guess, I am 10% confident that this might be Jack Hawley. When the human sees this, he can probably decide, okay, at least the model is making a prediction in a consistent category of humans. The second form we consider is by showing the most influential training examples. So if the model says, okay, I've seen this example that has this label before, then the human can decide whether this training example is actually relevant to the test example and make a decision based on that. And the last form we consider is by showing the most influential features in the test example. And when the human sees that, he or her can decide whether the model is looking at the right parts in the input and make a decision based on that. So these are the three forms of interpretation that we consider in this paper, but the general framework can be extended to other forms. So again, taking a step back, similar to before, interpretation is only part of the system, although people do kind of intrinsic evaluations of how they closely explain the predictions. But here, what we care about is still the human performance. And the goal of having interpretation in this setting is still to augment human decision-making and eventually improve human performance. So this naturally leads to the evaluation framework that we propose in this paper, which looks like something like this. So So we collect a bunch of input examples, show them to a bunch of human users, and we change the interpretation that we show to the users and see how their performance changes correspondingly. This is basically what we do in this paper. Next, we'll switch gears and talk about the details of the experiments. The task that we use is called Quizbowl. It's a trivia question and answer game played by many students around the world at different levels. It's a very active community, so about 10,000 new questions get written every year. So it can be played offline like this, like with two teams sitting together and the moderator reading out the question. It can also be played online using an interface like this. So again, the question is read out word by word. And the interesting thing about Quizbowl is that you can buzz in at any time, like the user did just now, and provide an answer. If your answer is correct, you get 10 points. If otherwise, you lose 5 points. And this one, I think, is answered very quickly. Yeah. So the competition is try to answer accurately with as little information as possible. So this is the first characteristic that we care about Quizbowl. The second thing we care about Quizbowl is how the sentences in the questions are ordered. They are ordered by difficulty. So the hardest clue will actually appear at the beginning. For example, in this question about dog Engelbart, the first sentence in the Quizbowl question is talking about a very specific life event. But next, we move on to some easier clues, such as this sentence talking about how the mouse evolved over time. And the last sentence will usually be very easy. Like, it's just asking who is the inventor of mouse. Again, the challenge is to answer as quickly as possible and also accurately. So the human component in our evaluation framework is just Quizbowl players. How about the model component? So what we have here is a system called Quanta. It's kind of a state-of-the-art Quizbowl model. Showing here is Quanta beating a group of top human players back in 2017 with the score shown in blue by Quanta and green by humans. Quanta is based on Elasticsearch, which is a very simple model, so I'll just skip the details and talk about the interpretation that we can get from Quanta. Again, we will consider 3 forms of interpretation as we mentioned before. The first form is the alternative answers. So we'll just show the list of guesses considered by Quanta at the moment and the corresponding confidence scores. So by looking at this list of guesses, what the human can get are things, for example, like, is this list stabilizing towards the end of the question? Are the gaps between the top scores increasing or decreasing? And those might be indicators of whether or not the model is making a confident prediction or not. The second form is by explaining by examples. So we're showing previously written Quizbowl questions and also highlight the most important keywords. So we have 3 lines here. Each line is a snippet of one training example. So by comparing these training examples to the current question, we can decide whether it's actually looking at relevant information and make a decision based on that. The last form of interpretation is explaining by features. So we're just highlighting the most important keywords in the question. So the kind of information we can use here is whether the system is actually looking at the key named entities instead of looking at like stop words and stuff like that. So putting all 3 forms of interpretation together, we have an interface like this, which basically mimics the layout of the previous interface I showed. So again, we have question updated word by word in the center, and we have 3 forms of interpretation arranged around the question area. So all the interactive, interaction mechanics stays the same. All 3 forms of interpretations are updated dynamically and periodically. And like buzzing, answering, things like that all stays the same. So it's familiar to Quizbowl players. So each interpretation can be turned on and off independently. So we have 3 forms. So we have 2 to the 3rd power, 8 total combinations, including no interpretation at all. Just to reiterate, we collect a bunch of Quizbowl questions, show these questions to Quizbowl players and the system Quanta. Quanta will make a prediction and explain the prediction using 3 forms of interpretations and we'll see how the player's performance changes. So the data we collect from this process has, so we recruit 30 experts, so Quizbowl enthusiasts, 30 novices, mechanical Turks. We write 160 new questions that the community has never seen before, and we have 8 combinations. So this is the data set we use, and next we'll talk about the analysis of this data set. So the first thing we did was pretty standard. We just do a regression analysis using this data set. We extract features from all 3 components. Basically, these features will describe the ability level of the player, the difficulty of questions, and what kind of interpretation was enabled at that point. We have a linear model because we want the coefficient to be explainable. We use that model to predict whether this answer given by the user is correct or not. And after training on this data set, the coefficient will explain which features are important. So the first thing we look at is how, so we have 2 groups of users, right? So what we want to see how much these interpretations affect these users. So each bar is the coefficient of 1 player with novices on top, experts below. The solid black line shows the bias term, which is the baseline performance. So it's natural that we see a higher baseline performance from the experts. The interesting thing is the red solid line, which shows the coefficient of combining all 3 interpretations. So we see that novices are actually affected more than the experts. Next, we'll do a finer grain analysis by looking at the individual interpretations. So the interesting thing here, so the length of the bar shows the magnitude of a coefficient. The longer the bar is, meaning this interpretation is more helpful in improving the probability of answering correctly. The interesting thing here is not only they are affected differently in terms of magnitude, they also have different preferences. So novices prefer evidence over highlight, so they find showing the training examples more helpful, but this is actually the opposite for the experts. So what happens when we combine them? For example, when we combine guesses and highlight for the experts, there's actually a bonus effect. And the nice thing is this kind of bonus effect is actually quite consistent in the expert group, which means explaining the prediction from different aspects actually help them significantly in making a better judgment. But this is not always the case for novices. So, okay, I should say the blue bar shows a positive bonus effect. The red bar shows a negative bonus effect. And sometimes the novices are actually negative affected. Exactly why this happens is not quite clear, but we conjecture 2 reasons. So one is that there's actually an information overflow. So the novices might not be able to process the amount of information shown on the interface. The other reason, which we'll see some evidence for next, is that the novices are actually too trusting. So when they see a lot of information shown about the predictions, they tend to just trust the system and play very aggressively. So this is showing the buzzing position. Like recall, we care not only about accuracy, but also speed. So buzzing earlier means the player is playing very aggressively. The blue box shows us the buzzing position when a certain interpretation is enabled. The red box shows when it's disabled. So both user groups become more aggressive with interpretations, but the novices are affected more. We'll see one specific example why this happens. This is actually a failed interpretation, which means the model is actually making an incorrect prediction, but some experts are actually fooled into believing the model. So the question is actually talking about the author of a book with a certain preface, but the evidence, so the previous question is talking about the author of that preface. So if you don't have enough time to process this and just look at, okay, it seems that the keyword matches, you might just trust the model. So interpretations can be misleading at times. We have a slightly more detailed analysis than this in the paper. I'll refer you to that. So I guess I'll just wrap up with a few interesting takeaways. So from the regression analysis, we see that interpretations affect different user groups differently. So you really want to design the interpretations for your specific user group. These things are supposed to help us understand model predictions, but they can be misleading at times. Like from the machine learning community, people are talking about interpretations not being faithful to your predictions. And this is kind of that type of example on the human side. Particularly, novices can be too trusting, especially because our system has a very high performance. They tend to just trust the system. So we actually might want to generate examples and train the humans in the loop to make a better judgment. So all of our experiments are designed around Quizbowl, but the general evaluatory framework does not make any assumption about the task. We also don't make any assumption about the underlying algorithm that you use to generate these interpretations. Quizbowl is just very interesting because computers and humans show different skill sets, so we use that. The last thing is, something I didn't mention is, in the experiments, we randomly select the interpretation to show. But there is still room for improvement if we select the interpretations dynamically and intelligently. So the goal will be to optimize human performance. So I'll have a shameless plug here. So if you're interested in this work or like Quizbowl related research in general, definitely visit quanta.org. We have other human-computer interaction things like using the computer to generate more challenging questions and help users write questions. So definitely visit that. I think that's my talk. Thanks. There's
it's a great talk. I find it intriguing on number 3 here that we have a system that's built to assist human decisions, and we decided to train humans know how to use the system.
Right.
I was thinking that what are those ways that we can actually have the system adapt to human. Like, so for example, if we are interacting with a novice, maybe, so for example, the confidence level we display should be different.
right. Yeah.
So,
I agree. Yeah. So that's kind of like the 5th point that was. So like by the 5th point, I was basically thinking. So I guess I'm not thinking about changing the interpretation directly, but changing what type of interpretation to show. For example, if we see like novices can be misled by evidence, that we might choose to hide that. Things like that. Yeah.
Really interesting talk. I have a quick question. So do you have any insights into or any observation on how your human players actually use the interpretations you have, or did they develop any strategies of utilizing those like interpretations? Because in your example of failure cases, I can see you are suggesting that the users were only looking at the keywords but not reading the whole thing. So I wonder if you have any insights into that.
Yeah, so we talked to some Quizbowl players offline. It seems that like whether or not the highlighted words are named entities versus like meaningless stop words seems to be a strong indicator. Like personally, I stare at this interface for a very long time, but I'm a novice, so I'll just try to see if the training examples actually are relevant to the test example. So there are like some strategies that they develop like over time.
Very interesting work. I was wondering if you can say a little bit more. You're saying here that novices can be too trusting and they can be fooled by wrong answers if they're well justified. Can you say a little bit more about if experts fall for that sometimes, or
Yes.
what is how do they compare experts and novices for accepting false positives from the system?
Yeah, so that's a good question. So we actually have a slightly more detailed analysis, like something like this. So this is I will do it quickly. So this is basically breaking down the buzzing projection thing based on the outcome of the guess again. So this density thing is showing the density of buzzing positions. So this is for experts. So even for experts, they will play more aggressively. And they sometimes get things wrong. This is included in the paper if you don't have enough time to read this. Yeah, yeah, expert can be fooled also.
So great work, very interesting. But I was just wondering how different is it to train a model versus train a user?
Oh, I think it's very different, right? So Yeah, I don't think I have a good answer to that. I guess personally, I feel like it's much more difficult to train a user. I mean, training a model to select interpretation can be formulated kind of as a reinforcement learning problem.
Yeah.
But I don't have a mental model for training humans.
Okay.
Okay, I guess time's up. So let's thank